Now, moving on to the redox reactions and basically electrochemistry. So, this is basically, if you do your labster activity, we will you will actually encounter this one again. So, I do suggest that if you have your laboratory right now or this week, the labster activity for this week is about electrochemistry, and this is about, basically, this is the topic here on the labster. Now, electrochemical reactions are processes that are oxidation reduction reaction. So what is an oxidation and reduction? So for an electrochemical reaction, from its name, electro and chemical, so in here the reaction produces changes or an electrical current, or it is mainly involving, of course, transfer of electrons. Actually, the same with all other reactions, there's a transfer of electron, but for electrochemical processes, this is more apparent because you can actually generate current here. So how do you generate a current? A current is a moving charge. So it happens when one of the reactant loses an electron, that is, it undergoes oxidation, and another reactant undergoes reduction. So that means it gains electrons. So basically, there's an electron transfer between the two reactants. So the energy released by a spontaneous reaction is converted to electricity. That's why we call it electrochemical. And this is the electrical energy is used to cause a non-spontaneous reaction to occur. So let's say, for example, the magnesium metal and an oxygen gas. So again, nawawala, I have missing arrows, but anyway, so you have here your magnesium loses two electrons. So 2 electrons each, so that means you have a total of 4 electrons. And this is the oxidation half reaction, which loses the electron. And your oxygen is the one that gains that electron. So the magnesium, the amount of oxygen electrons that the reaction or the reducing agent, basically the magnesium, so basically the amount of electrons that magnesium lost must be the same amount of electrons that your oxygen gained. So that is for the reaction to balance. So you have 4 electrons that was lost by the 2 magnesium atoms, and you have 4 electrons gained by the 2 oxygen atoms. So that's oxidation and reduction. So oxidation is a lost and reduction is gain. So basically there is an mnemonic for that. I tend to use oil rig, OILRIG. Oxidation is loss, that's oil, and rig, reduction is gain. So that's the mnemonic that I used. So as you can see here, you have oxidation numbers. So the oxidation number of magnesium is 0. Oxidation number of the oxygen gas is 0. But when it undergoes the reaction, it becomes a positive 2 and a negative 2, respectively. Now, what is the oxidation number that I had been saying? The oxidation number is the charge of the atom that the atom would have in a molecule or an ionic compound if the electrons were completely transferred. So basically, this is similar to the Lewis, the formula charge of your atom. If you remember when drawing the Lewis structures and the formal charge, so it's basically similar to that. Now, your oxidation number for free elements is always 0. This is for pure substances or pure elements. Sodium, beryllium, potassium, lead, hydrogen gas, oxygen gas, phosphorus, all have oxidation states of 0. Basically, neutral compounds, neutral substances have a total oxidation number of 0. So for the monoatomic ions, the oxidation number is equal to the charge of your ion. So for example, the lithium ion is +1, the ferric ion is +3, the oxygen ion is -2. Now, for some cases, this is the oxidation number of oxygen is usually -2, but that is not always the case. For example, in the hydrogen peroxide, the peroxide ion, for the peroxide ion, or rather for peroxides, the oxidation number of oxygen is always -1. And that's the reason why peroxides are very reactive, because oxygen do not want an oxidation number of -1. It prefers a -2 oxidation number. Anyway, so we have for hydrogen, it's almost always +1, except if you have a binary compound where the partner of hydrogen is a metal. So for example, lithium hydride. So if you remember from the name itself, hydride, the hydrogen here acts as the non-metal partner, so it has an oxidation number of -1. But for example, hydrogen bromide, HBr, hydrogen is the one that functions as the metal part, since bromine is the non-metal, so you have an oxidation number of +1. So basically, oxygen is more flexible in terms of its properties. It can act as either a metal or a non-metal. So you have group 1A metals are +1, 2A metals are +2, and fluorine is always -1. So the sum of the oxidation number of all the atoms in a molecular ion is equal to the charge on that molecular ion. So let's say, how do you balance a redox reaction? For example, the oxidation of iron to Fe, iron 2 plus to iron 3 plus by dichromate in an acidic solution. So first, we need to get the unbalanced equation in the reactions, or the unbalanced equation for the reaction in your ionic form. So we said that, again, I am missing my arrows, but anyway, so you have your iron, the reactants as iron, these are the reactants. Fe2 plus Cr is the dichromate, so this is the dichromate. It becomes iron 3 plus, so Fe2 plus to Fe3 plus. And this one is, you have your reduction of chromium, so you have your Cr from the dichromate polyatomic anion, you have the Cr3 plus. So separate the equation into the two half reactions. So you have your iron. So the one that undergoes oxidation is the iron. So iron 2 plus to iron 3 plus. Oxidation number is +2. It becomes +3. So that's actually one of the ways how do you know which one undergoes oxidation, which one undergoes reduction. So oxidation, if your oxidation number increases, it undergoes oxidation. If the oxidation number decreases, it underwent reduction. So the oxidation number of the chromium in a dichromate ion is +6. So how do you know that? Remember, your dichromate has a charge of -2. So the total charges, or the total if you sum up all the oxidation numbers of each atom in your dichromate ion, that the sum must be equal to -2. So if we have oxygen, which is usually -2, so we have 7 oxygen. So 7 times -2, that's a -14. And then you have 2 chromiums. At first, we do not know what is the oxidation number of chromium. So we know that the oxidation number of oxygen is -2, so times 7 is -14. So the total must be equal to -2. So we are missing actually +12. So because the number that must be added to -14 to have a sum of -2 is actually 12. So 12 must be the total oxidation number for the 2 chromium. So we have 2 chromiums. So 12 divided by 2, you have 6. So basically, that's the oxidation number of your chromium in the dichromate ion. And now, based on our given equation, the dichromate becomes chromium 3 plus. So you have from +6, it becomes +3. So the oxidation number is reduced. So you have basically reduction. So dichromate underwent reduction. So after that, we need to balance the atoms other than the oxygen and the hydrogen. So balancing redox reaction is a bit more difficult than the usual reaction that we have. So in here, we do not need to consider, or rather we will consider oxygen and hydrogen, but that is on the last step. So we balance first all the other atoms. So we have 2 chromiums in the reactant side, so it must have 2 chromiums in the product side. So that's to balance it. Now, in acidic solutions, we add hydrogen. For acidic solutions, we have water to balance oxygen atoms and H plus to balance H atoms. So when we say acidic solutions, we add H plus, this is the protons, or rather they call it hydronium ions, in the reactant side because this is acidic. So if our reduction equation, initially you have your dichromate to become Cr3 plus. So we add hydrogen ions on the reactant side and water in the product side. So why water? Why not just plain oxygen? So because these are equations or reactions under in the solution. So basically, water is everywhere in a solution. So we just have water present here, and we say it's the reaction occurs in an acidic solution or in an acid. So you have here H plus, because again, when we define acids as solutions, or well, basically solutions that have an excess of the hydronium ion. So we have hydronium ion present in an acid, so it's present in the reactant side. And since the whole reaction occurs in a solution, you have water. We add water on the product side because we want to balance the oxygen here. Because remember, our original reduction equation, you have the chromiums, but you do not have oxygen on the product side. So to balance that, we just have water on this side. We do not use negative we do not use hydroxides. We have water, not hydroxides. Why not hydroxides? Because again, this is an acidic solution, not basic solution. Now, after that, we need to balance the electrons of each half reactions. So iron, Fe2 plus or Fe3 plus, this iron lost 1 electron. But for the dichromate, you have actually, since it's plus 3, remember our previous equation, it's plus 6 to plus 3. So, and there are 2 chromiums. So, the 2 chromiums must have, each gains 3 electrons. So, it must have 6 electrons. So, 6 electrons must be added to the reduction equation for the dichromate to become Cr3 plus. And to balance it, where does the 6 electron come from? The electron comes from the iron. So that means we need to balance the electrons. So this is the additional step in balancing redox reaction, because not only do we need to balance each individual atoms, we also need to balance the electrons for the oxidations and the reduction. So we need to multiply iron by the oxidation reaction here by 6. So we need to equalize the number of electrons of the 2 half reactions. So we multiply it by 6. So you multiply the oxidation side by 6. So we now have a balance. Well, basically, two half reactions. This is one half reaction. This is another half reaction. Both of them have the same number of electrons. Now, we now add the 2 half reactions together. So it's easier to just separate the oxidation and reduction equations first and balance everything before we synthesize them into a single redox equation. So the oxidation side, we have iron, 6 iron 2 plus to become 6 iron 3 plus the 6 electrons it lost. And for the reduction side, we have the 6 electron it gained plus the dichromate, of course, and the additional 14 hydrogen. This is just to balance our oxygens and hydrogens on both sides. And then you have the 2 chromate, Cr3 plus atoms, and you have your 7 water molecules. So we just add them together. So again, we cancel out the 6 electrons. Our balanced redox reaction is 14H plus Cr2O7, or rather dichromate, plus the 6 Fe2 plus to form 6 Fe3 plus 2 Cr3 plus ions and 7 water. So basically, this is your balanced redox reaction. So it takes a much greater number of steps. I do suggest you do the Labster exercise, because Labster has its the exercise in Labster also has, that is in from your laboratory activity. It has activities on balancing redox equations. Now the last step is to actually verify that you have the number of atoms and charges are balanced. So again, the charges on the reactant side, we have 14 positive ones from the hydronium ion, 14 times 1, minus 2, that's the charge of the dichromate, times 6 times the charge of your iron. So you have 24. So on the reactant side, this is 6 times 3 plus, so 18 plus 2 times 3 plus, that is 6. So 18 plus 6, so you have 24. So that's balance. And then now this is for acidic solution. If you have a basic solution, so you just add the hydroxide ions to both sides of the equation for every H plus that appears in your final equation. So for this one, if we say that this occurs at, for example here, this reaction occurs in a basic solution. So sometimes redox reaction occurs in acidic solution. Sometimes it occurs in a basic. So for a basic solution, you can just follow this step. So that you only need to actually some books will tell you this is the way to balance for acidic, this is the way to balance for the basic, but the easier way is just memorize one. For example, just memorize the steps for balancing in an acidic solution and then convert it to a basic solution. So how do you do that? You add hydroxide to both sides of the equation. So for example, given this reaction in acidic medium, if this one occurs in a basic medium, if you have 14 hydronium ion here, you just add 14 OH on this side of the equation and another 14 OH hydroxides on this side. So you have 14 hydroxide plus the hydronium ion. So basically, we can cancel this out as water because again, hydronium ion plus the hydroxide ion, it forms water. So the 14 hydronium ion here plus the 14 hydroxide, it becomes 7 water molecules, and then you have 14 OH on the product side. That is not cancelled out. So you will have then 7 water molecule on this side and another 7 on this side, so you can cancel out the water. So the reaction here, if you convert it to a basic reaction, you will have dichromate plus 6 iron to form 6 iron 3 plus 2 chromate plus 7 instead of water. This is 7 hydroxide molecule. So basically that's that is your balance. Actually, sorry, it's not, we are missing pala the 7 water. So 14 hydronium ion plus 14 hydroxide, that is 14 water. So let's I think I can let's write it para mas madali. Okay. Okay. So let's try to write this one. Okay. So you add here your 14. Why is it's not? Okay, it should stick. Okay, it won't. Ayaw niya. But anyway, so that is what you just have to do is just to balance it by adding the OH molecules. Okay? So anyway, so let's see, for example. So what's the balance ionic equation to represent the oxidation of iodide by permanganate in a basic solution to yield the molecular iodine and a manganese oxide? So this one is in a basic solution. So this is a good way to practice balancing the redox for a basic solution. So you have your, again, we follow the steps in balancing redox equation. So this is for the acidic solution. So you don't have to learn the two, because some books, some references will tell you, oh, this is for the acidic, this is for the basic. But one way is just to simplify life. You just remember one and then convert one from the other. But anyway, so you have the unbalanced equation. You have manganese oxide. So you have permanganate plus iodine to form manganese oxide plus permanganate plus iodide to form manganese oxide and your iodine. Now the oxidation here is on iodine because the oxidation number of iodine initially is -1, it becomes 0. So it's a loss of electron, and for the reduction, it's the permanganate. So manganese here is +7. Why is it +7? Again, oxidation number of oxygen is -2, and we have 4 oxygen. That means this one contributed already -8. If you have a charge of -1, so we are missing 7 plus 7. So +7 minus 8, that's -1. So that is why it's the reduction, or rather the oxidation number of manganese is 7, because it's the number that we need to add to -8 to get the charge of the molecule, which is -1. And then for the manganese 4 oxide. So as its name suggests, manganese 4, the oxidation number is 4. But if you want to calculate here, this is a neutral molecule. So this is the charge of the oxidation number of oxygen is -2 times 2. So you have -4. So in order to balance it, you need +4 for the manganese. So next we need to balance the half reactions. So we have iodine, I2. So we just add 2 in the iodide. Now, we balance now the charges. So for the 2 iodide, it lost 2 electrons. For the other half reactions, so we need to balance for this half reaction, so +7 and +4, that's actually 3 electrons. So for this reduction half reaction, we need to balance now the oxygen atoms in the reduction half reactions. So since the manganese is already balanced originally, so we just need to balance the oxygens. So this is basic. So well, if we can just add hydrogen, water, or H+. So in here you have your water. You add water in your in the side that is missing an oxygen, because the reactant side is 4 oxygen, the product side has 2 oxygen. So you add water because it's missing oxygen. So you add water, two water molecules to be exact, to balance the missing 2 oxygens from here. And then to balance the hydrogens, we just add 4 H+, because again 4 hydrogens. So this is this procedure is for balancing redox reaction in acidic solution. But remember, this must be in basic. But later we will come to that. So you have your balanced reduction equation. If you add the electrons, permanganate plus the 4H plus the 3 electrons that must be added to become manganese 4 oxide and the water. Now you add the 2 half reactions. You have we need to balance the electrons. We have 2 electrons in the iodine side and we need 3 electrons on this side. So to balance it, we just multiply the oxidation half reaction by 3 and the reduction half reaction by 2. So both of them must have 6 electrons, which can be cancelled out. Now you have your equation in acidic medium. But again, this is basic. So in order for us to convert this one in an acidic medium, so this is the balanced redox reaction in acidic medium. But for it to become a basic, to balance it in a basic medium, so if you have here 8 hydronium ions, we just add 8 hydroxide ions on both sides. So I add 8 here, add 8 on the product side as well. Now hydronium ions plus the hydroxide ions becomes water. So you have 8 water. Basically, this becomes water molecules. You have 8 water molecules, which can be cancelled out because you have 8 water molecules in the reactant side and 4 water molecules on the product side. So we cancel out 4 from this side. So we have 4 water, and then of course there's no longer water here, but the remaining hydroxide ion is left on the product side. So this is the balanced redox reaction on a basic medium. So from the acidic, you just need to remember how to calculate, how to balance it from the acidic, and then convert the balance equation from the acidic to the basic. So in the next part, we will discuss about galvanic cells.